It is now October the 2nd. How did that happen? Did any of you tweet at the guy from Green Day to wake up? Because September had ended? Yeah, thank you. That's all that was worth. We're going to begin today where we started last time, where we're discussing the malonic ester synthesis and the acetoacetic ester synthesis, which are really syntheses beginning with those starting materials and leading to alpha-alpha dialkylated products. The product of the acetoacetic ester synthesis in the end is going to be a ketone. The product of the malonic ester synthesis in the end is going to be a carboxylic acid. And we're using these methods as cheaper and more reliable workarounds to enolate alkylation chemistry. We'll avoid undesired ether formation, and we will gain unambiguous control of regioselectivity, but with very cheap reagents. We don't have to use LDA at all. So as we were talking last time, I showed you the conventional approach for making this ketone, where we would start with acetone, and then we would use our reversible enolate formation to deprotonate the alpha proton, and then do the SN2 reaction to install one methyl group. And then, under the hope that we could reliably generate the more substituted thermodynamic enolate, we would do it again and get this product. And you can assume that those conditions will work. But the author of your text is a synthetic organic chemist, and Professor Smith cares a lot about efficiency and yield. And so she uses these two reactions that we're going to talk about now as a way to show you a better way to make something, and as a way to introduce an important thing that will show up all over in biology and biochemistry, which is this concept of decarboxylation. So we talked last time, you start the acetoacetic ester synthesis with acetoacetic ester, which is a beta keto ester. The ketone is on the carbon that is beta to the carbonyl carbon. We talked about how the proton that's alpha to 2 carbonyls has a really low pKa of 13. So the overview is we're going to first completely 100% deprotonate that alpha carbon to generate an enolate, whereupon we will introduce the methyl bromide or whatever alkyl halide we want. The reaction is an SN2 reaction. Usually this alkyl halide should be primary, though there may be some exceptions to that and some problems that you do. Obviously, you wouldn't ever want to use a tertiary alkyl halide because you learned in 351 that those don't do SN2 reactions. After we complete that first SN2 reaction, we have what I'll call the monoalkylated beta keto ester, where we have the one alkyl group on the alpha carbon. We still have a proton there that's still acidic. It's still between 2 carbonyls, still alpha to 2 carbonyls. So we can, with the same base, with another equivalent of base, sodium F oxide, we remove that proton to generate this enolate. And that's where we were when we stopped last time. Step 4 will be to introduce, again, another equivalent of alkyl halide. For our purposes, since our target is this molecule in which we have 2 methyl groups on the same alpha carbon, we will use the methyl bromide electrophile. Of course, if we wanted to make something different, we could do so. Doing that will give us the dialkylated beta keto ester, in which there are now 2 methyl groups on that alpha carbon. And following along, this alpha carbon here in our desired product is the same as this alpha carbon here. But as I've tried to tell you, the ester carbon doesn't end up in the final product. We lose it after step 5. Okay, but before we do that, any questions? Sort of standard enolate. Yeah, go ahead.
So let's say you have 2 different groups, like a methyl group and then another group that's like a different carbon group.
Sure.
Is there a preference on like which one to do first?
Which one you should do first? No.
Okay.
Yeah, the reaction works well enough that if those were 2 different groups, there'd be no reason to put one on versus the other first. Yeah, go ahead.
Those can absolutely not be vinyl or
But, right, because, good question, because the reaction is SN2, you can't use RXs, alkyl halides, that don't work in SN2. So no tertiary alkyl halides. Also, you've learned that sp2 hybridized halides like vinyl or aryl halides don't work. So that's a good limitation. Okay, others? I feel like that's in the way. Yeah, go ahead.
So like on the homework there was a problem where we had to use LDA first and then do the sodium oxygen, the NaOET.
Okay.
And so is that possible to like switch the order?
I think the problem you're referring to may not have been on this starting material, though.
Right. So like could use LDA on that first.
Oh, okay.
And add an alkyl halide to the
You want to do something here?
yeah. And
Okay.
then attach use the other reaction.
Okay. Yeah, let me address that question real quickly. Let me just scroll down and do that. The question is, if you have something like this, you've got two different kinds of alpha protons. And the question is, if I use LDA, could I remove orange alpha proton? I want to contrast this question with this one that we dealt with previously with LDA versus sodium ethoxide. The issue of LDA versus sodium ethoxide and enolate regioselectivity is really only one that matters when the protons have similar pKa's. So the orange alpha proton over here has a pK of around 20 because it's alpha to a ketone. Likewise for that one. Orange alpha proton here has a pKa of around 20, but because purple alpha proton is between two carbonyls, it is much more reactive and has a pKa of 13. This one is much more acidic. And it turns out that LDA's kinetic preference for the less sterically hindered proton will not overwhelm this 10 million times more acidic effect. Okay? So even if you were using LDA here, because of the massive difference in acidity, the LDA versus sodium ethoxide preferences are overwhelmed by the difference in acidity, and the most acidic proton is the one that is removed. So even using LDA as a base, you're still going to get that one. Okay? Because of that, it would actually be pointless and way too expensive to ever use LDA up here in this acetoacetic ester synthesis, because you can do the job with a much cheaper base, and LDA is only ever going to remove that proton anyway. Now, if you wanted to put other groups out here, I will show you how to do that, but that will probably take till chapter 18. Yeah. Okay, others? It's good issue, yeah.
You wouldn't happen to be recording this, would you?
I believe I did press record. Yes, the little square is there and we got audio, so thanks. We are live. What else? Yeah.
So we can't work with tertiary groups without.
Secondary is okay. It's easy and fast if it's primary. For secondary, you can assume that it works, though experimentally sometimes there's problems. All right, so now I want to talk about how we get from this alpha-alpha dialkylated beta ketoester intermediate to the final ketone product. And that's that's all one step. That's this last step 5. ester hydrolysis first and then decarboxylation. So all of what I will draw from here on out is step 5. It's just there's multiple things that occur in step 5. So acid catalyzed ester hydrolysis. What product will that give us? That should replace the OET group on our ester with an OH group to give us this product. And this is a beta keto acid because here's the carbonyl carbon, alpha carbon, and beta carbon. Beta to the carboxylic acid is a ketone. Now, that is just ester hydrolysis. I'm not going to draw the mechanism of that for you because you saw that in chapter 16 and you practiced it, so we won't talk about it. Effectively, you protonate the carbonyl oxygen on the ester first, then water attacks to get a tetrahedral intermediate, proton transfer to trade who's the good leaving group, then electrons kick down and kick off ethanol as a leaving group is what's going on. That happens first. This is the intermediate, and it doesn't last long because this now does what we will call decarboxylation. So that's sort of the second phase. Phase 5A is ester hydrolysis. 5B is decarboxylation. Yikes, my arrows are not going to places where there is room to draw things. The decarboxylation product here will look like this. There are my 2 methyl groups attached to the alpha carbon. Here's what used to be the beta carbon, and then over here is what used to be the carbonyl carbon, I'll call it C, and that is CO2, which is lost, meaning it goes away with the air. The product of step 5B, or phase 5B, is, you will note, an enol. And the enol, as you've noted before, as we talked about earlier, is the less stable version of its ketone tautomer. Remember, tautomer is the word that we use to describe an isomer that differs in the location of a pi bond here between these 2 carbons, here between carbon and oxygen, and a proton here on the oxygen, here on the alpha carbon. That's the enol form, and the product is the keto or ketone form. And so step 5C is, you got it, tautomerization. Okay? So tautomerization you have seen before, ester hydrolysis you have seen before, decarboxylation you haven't. So let's zoom in on decarboxylation. And I want you to pay attention to this structural pattern of a beta keto acid. Intermediation, what the heck does that mean? I must have been saying decarboxylation at the same time as I was trying to write intermediate. I hope you're not writing down everything that I write down. That's kind of, I don't know what he meant by that, but it might be important. Let's get it. The beta keto acid intermediate is very important to recognize as a structural pattern for when decarboxylation can occur. All right, so let's draw what that is. I'm going to scroll down because I'm out of space for a mechanism, and I'll show you the mechanism of decarboxylation. So here is the beta keto acid. I'm going to draw it in a slightly different way. I'm going to draw the OH group for the carboxylic acid pointing sort of upward. I'm doing this for reasons that will become clear in a moment, but notice that that just involves rotation around a carbon-carbon single bond, so it's not that big of a deal. Here is your beta keto acid. Again, I repeat that on the beta carbon is a ketone. You can do decarboxylation under a couple of different conditions. We're using acidic conditions here because we needed to hydrolyze the ester. So I will show you a mechanism for decarboxylation under acidic conditions. Notice that the carbonyl oxygen on the beta carbon is 1, 2, 3, 4, 5, 6 atoms away from the hydrogen. They form possibly a 6-membered hydrogen-bound ring. It's not too much of a stretch to imagine this electronegative oxygen with a partial negative charge on it, hydrogen bonding with this hydrogen that's on the acid. I'm going to sneeze, sorry. Excuse me. Try not to explode. All right. I have a brother-in-law that does sneeze impressions, actually. He's listened very carefully to the characteristic sneezes of his family members, even deceased relatives, and he can reproduce them pretty effectively. The trick is getting himself to sneeze, so he'll sit there and pull his own nose hairs until he has to sneeze. That's way too much detail. Sorry. Right. So the carbonyl oxygen is hydrogen bound with the acid proton. Now let's imagine what would happen if it stole the acid proton completely. So let's show carbonyl oxygen removes a proton from the acid. That would lead to a buildup of negative charge on this oxygen, right? That can then act, these electrons, as negative charge is building up on this carbonyl oxygen, can act as a kicking off group to kick off the alpha carbon. Those electrons will go to form a bond between alpha and beta carbons, and then the pi bond between the beta carbon and the carbonyl oxygen will break. I know you hate that, but if you follow all the arrows, it leads to that enol product that I showed you. Now, that was kind of a lot to talk through. What makes this happen? This is more difficult than you're used to because this is an intramolecular elimination reaction. CO2 is being eliminated from the molecule, but it's not clear where it begins. It sort of occurs in a cycle, and it's not totally clear what the initiating factor is. Really, as I said, under acidic conditions, you need heat to make this thing happen. I want to show you decarboxylation under basic conditions because that will give you a better feel for what's going on and where the process gets started. So under basic conditions, the carboxylic acid would be deprotonated. It would exist in its carboxylate form. And by basic conditions, we're really just sort of talking about conditions where pH is greater than around 5. Now, if we look at that, I'm going to argue that the negatively charged oxygen is a kicker-offer, much the same as we've seen before in a tetrahedral intermediate, which is why I'm going to color it pink. The carbonyl carbon here is much the same as the central carbon in a tetrahedral intermediate. And then I'm going to argue that all of this, I'm going to argue that all of this is a leaving group. And the reason why it's a leaving group has to do with the fact that this carbon that's going to leave is adjacent to a carbonyl, and a negative charge on that carbon could be stabilized by resonance. So watch as electrons kick down to form a new carbon-oxygen pi bond, and the leaving group leaves. And I will show the arrows this way, mostly to illustrate what I mean by leaving group and resonance stabilized. So, here is the new carbon-oxygen pi bond that we formed, similar to what always happens when we kick a group off a tetrahedral intermediate. And here is the leaving group. Lo and behold, it is an enolate. And the reason it can leave, the reason that alpha carbon can tolerate the negative charge is, of course, because that enolate is resonance stabilized. Okay? So effectively, what I've shown you here for the mechanism under basic conditions, those same principles are operating over here. The carbonyl carbon here is like the carbon in the tetrahedral intermediate. The oxygen is the kicker-offer. And then all of this is a good leaving group, only it picks up the proton while it's leaving to help it leave better. Okay, that is decarboxylation. That's, surprisingly out of left field, but it's crucially important in so much biochemistry. In fact, the CO2 that you're currently exhaling, you're exhaling because it has come off of one of these decarboxylation reactions in your mitochondria. So, kind of a big deal. There's some went, right? All right. Questions about decarboxylation? Yeah. It's okay. Whoever wants to go first, then we'll give you a
Under basic conditions, it's like, I guess if you were to do it in a lab, is as much heat required from like often
I don't actually know. It's a good question. I know that it can happen catalytically in your body at room temperature. Not sure. Good question. Yeah.
So does this just basically happen spontaneously if you deprotonate carboxylic acid?
Yeah, if you deprotonate the carboxylic acid, would it happen pretty much spontaneously? Yes. It will also happen if you don't deprotonate the carboxylic acid, but you heat it up. In other words, beta keto acids are not that stable. And we'll see that when we do the citric acid cycle. There is a beta keto acid, which some people don't even call an intermediate in the citric acid cycle because it spontaneously decarboxylates. Yeah. Others? Yeah.
So theoretically, under basic conditions, could the enolate, could that attack like another carbonyl?
Great question. Could the enolate that you form attack another carbonyl? The answer is yes. And this is a preview of something that happens in biology that we'll get to in chapter 18. I'll just briefly illustrate it here. Let's see. Yeah, this will be fine. Is it fine? Yeah, it's mostly fine. Here is an intermediate in fatty acid synthesis. It's a little bit different than the beta keto acid shown above because the group over here is a thioester, but it spontaneously decarboxylates via a similar method, like we've shown you, kicking off the enolate, and then the resulting enolate is a thioester enolate, and you lose CO2. I'm sorry I didn't give myself enough space there. And then, yes, biology uses the resulting enolate as a nucleophile in a subsequent reaction. I am dying to tell you what that reaction is, but I'm going to force myself to wait. Yeah. But biology will sometimes use beta keto acids like this as what I'm going to call masked enolates. And they sing, and then you have to determine which. It's a masked enolate because the enolate is hiding here, and is only revealed upon decarboxylation. And what initiates the decarboxylation is the kicker-offer oxygen. Okay, so other questions? All right, let's go back to our reaction scheme. We just talked about decarboxylation. So again, thinking through what we just talked about, here is the carbonyl carbon, here is the kicker-offer oxygen, here is the leaving group, and the leaving group picks up a proton as it leaves. And that gives us the enol as a leaving group. And then here's your new carbon-oxygen pi bond, which just happens to be CO2. The next step is enol to ketone tautomerization. You have seen that before, so we don't necessarily need to talk about it, though I'll give you just a hint of a review, and then you can go back into your notes from earlier on in this chapter and work it out. Probably the best and easiest way to do this is to reflect on the fact that the enol has a resonance structure that looks like this, that puts negative charge on the alpha carbon. So you would first protonate on the alpha carbon using the acid that you have used to catalyze everything here, and that will get you to this oxonium ion intermediate, and then I'm going to stop there and you can show how removal of the proton on, okay, fine, it's going to take 2 seconds, I'll just do it. That's not a very nice arrow. There we go. That's the tautomerization step. Okay? So that's the acetoacetic ester synthesis. Importantly note, what did we do? We started with the 3 gray carbons here. Those three gray carbons are still in our product. I'll highlight them here. We installed 2 new alkyl groups. I need a color for the alkyl groups. We'll use this light purple. And importantly, we lost CO2. Okay? The carbon from the ester gets lost as CO2. Convenient way for doing this. By the way, if we had not wanted to put on the second alkyl group, we could have skipped steps 3 and 4 and proceeded directly to step 5. All right, we're going to make it worse before it gets better. First, I need to show you how we do this with malonic ester. So we'll do the exact same reaction, only we're going to use the malonic ester as a starting material. The malonic ester is interesting because both carbonyls are actually esters. So we would call malonic ester an example of a beta diester. But like the acetoacetic ester, the carbon in the malonic ester is likewise very acidic. Sorry, the alpha protons are likewise very acidic. I'd have to look up what the pKa's are. They're probably greater than 13, but still pretty low. So let's go ahead and do the exact same thing. We're going to use sodium ethoxide to deprotonate. We're going to use methyl bromide to alkylate. Then we're going to do it again, deprotonate and realkylate. And if you're following along, then that should give us the following product. We haven't messed with the esters on either side, but we did install 2 new methyl groups on the alpha carbon. Okay? So this is our alpha-alpha dialkylated diacid intermediate. Now again, we're going to do step 5, which is strongly acidic aqueous conditions with heat. And that's going to proceed in 3 phases. You're going to get first ester hydrolysis. Now, we can't hydrolyze esters selectively under acidic conditions, so we expect both esters to be hydrolyzed to carboxylic acids. So unlike before where we had a beta keto acid, now we have a beta diacid. But this is going to decarboxylate under acidic conditions in exactly the same way as we saw previously. In other words, we're going to pick one of the two acids. It doesn't matter which. One of the acid OH groups is going to be the kicker offer. This is going to be the carbonyl carbon. This is going to be the leaving group, the one that leaves as an enol, and it's going to pick up the proton as it leaves. So what we will be left with after that decarboxylation step is the following enol intermediate, just like we saw above. Nothing really new here, only there are two OHs on the enol, whereas there was only one above. And then here's your CO2 that gets lost. There's the kicker offer oxygen, there's the carbon. Okay? And then step 5C is tautomerize to get to the more stable tautomer that has the more stable carbon-oxygen pi bond and the proton on the alpha carbon. Notice that the carbons that are there in the product, these two, were also there in the starting material, and these other two carbons we lose to CO2. So for the malonic ester synthesis, it's exactly the same as the acetoacetic ester synthesis, only our product is an alpha-alpha dialkylated carboxylic acid rather than a ketone. Okay? Questions about that? Now, which one should you do? Well, it depends. Do you want a ketone or a carboxylic acid? That's going to depend on the synthesis problem. Now, what I want to do is we're going to do some where we make rings, which I know you hate, and we're going to do some where we think backwards, which I know you also hate. So, hate squared. All right. Behold, I want you to make that from, let's make it even worse, shall we? 7-membered ring. I want you to make that from acetoacetic ester. Now, remember, the steps of malonic ester and acetic ester synthesis are as follows. Deprotonate, alkylate. Do it again if you want. Deprotonate, alkylate. Then hydrolyze the ester, decarboxylate, and tautomerize. And in so doing, remember that the 3 carbons of acetoacetic ester, including the alpha carbon that is present in the starting material, those are going to be there in the product. So pay attention to where that alpha carbon is and to where the ketone is, and see if you can find the alpha carbon and the ketone in the product. That alpha carbon is here and the ketone's there, right? So it's helpful if you know, okay, these 3 carbons were in my starting material. I didn't have to do anything to keep them there. Then look at what's not there in the acetoacetic ester starting material. For example, you've got 2 protons on that alpha carbon and only 1 in the product. And you also have in the product these 2 carbon-carbon bonds, which you're going to have to make. Okay? This is an interesting reaction in the sense that the alpha carbon is part of the ring, but then you've got to supply the remaining carbons in the ring. And I'm using the red squiggly lines to indicate I needed to have made this bond probably by one of those SN2-like alkylation steps. The final piece of the puzzle is to recognize that both of these carbon-carbon bonds are linked to each other. So what will be useful is to count the number of atoms in the chain that links the one carbon on one side of the alpha carbon to the other. We'll just use blue. 1, 2, 3, 4, 5, and 6. Which makes sense because it's a 7-membered ring and we already know where the alpha carbon is. All right? So, sometimes it can help when you're planning a synthesis to take just, rather than do it from the beginning, and I know your inclination is, because presumably you're all Sound of Music fans, and so you know that we start at the very beginning, which is a very good place to start. False. Not for synthesis. We start at the end. I mean, it's true that a 1,000-mile journey begins with the first step, but a 1,000-step synthesis begins with the last one, because you've got to know where you need to end up before you can know where to begin. So, let's remind ourselves, what is the immediate previous step in the malonic or the acetoacetic ester synthesis? It's tautomerization. So we want to step backwards from the ketone to the enol. Okay, that should be easy. So let's step backwards to the enol. That's going to look like this. And then we got to draw that crazy 7-membered ring. Okay, then what is the immediate precursor to the enol? Remember, in the enol step, we lose CO2. So the immediate, and remember that this is the leaving group. That's the carbon, that's the oxygen. So I'm just going to sort of write down, we're thinking backwards through the tautomerization step. We now need to think backwards through the decarboxylation step. There's going to be a new bond between what used to be our alpha carbon and the carbon of CO2. All right, this is the kicker offer oxygen. This is the carbonyl oxygen. That's the alpha carbon. Somehow I got to fit my 7-membered ring down here. But I'm going to still use the same colors that we've used. Here is the group that's going to end up leaving as the enol. That's a hard step for people to make. It's hard, I've observed for students in the past, it's hard to jump backwards conceptually through decarboxylation. Once you get there, it's a little bit easier because remember the previous step to that was ester hydrolysis. So the precursor to that intermediate should be this ester. Okay? Now if I compare where I am to where I need to be, I can see the core structure of the acetoacetic ester, and I notice I'm down to just those last 2 alkylation steps. So, let's think backwards, and these are retrosynthetic arrows. They mean we're thinking backwards. You have to be really careful when you talk about this that you don't think that you're doing the chemistry forwards, backwards. So what is that alkylation reaction? What would the starting material for that alkylation reaction have been? Let's suppose I want to make the bond indicated in red. What would the starting material have been? And I remember I'm only making that bond. The other one's there. So I need between the alpha carbon, I need 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Did I miss something? No. 1, 2, 3, 4, 5. 6, then what do I need on the alpha carbon and what do I need on carbon 6 to make this work? You need a halide, you need a leaving group. So let's put a bromine there. And then on the alpha carbon would be a negative charge. Then I can do an intramolecular SN2 reaction. If you want to see the forward arrow, it looks like that, and that makes the indicated bond. Okay? We're going to jump back a couple of steps because I know you know how to do deprotonation reactions. What do you think? And now we're ready to sort of think, fine. I was going to jump ahead, but then I lost my nerve. All right, so this is the precursor. This is the deprotonate step. This is the alkylation step. How do I get from my allowed starting material to here? What would I need to do? Go ahead.
Well, I had a question about that deprotonation step you just drew.
Sure.
How do you get whatever's flung off the hydrogens and not do anything?
Oh, good. So the question is, if I want to use a base to remove that proton, how do I not interfere with the SN2 reaction of that alkoxide with the leaving group? You do it carefully and you pray hard, noting that the proton is quite a bit more acidic, and usually proton transfer reactions are really faster than SN2 reactions. So that is a potential complication. You mostly just hope for the best. And for our purposes, we assume that it will work. Now, what do we do here? What do we need to do to this starting material to get to this product? You first deprotonate with NaOET, and then what is the alkyl halide that I'm going to use? Yes, 1, 2, 3, 4. Oh, did I lose a carbon? 1, 2, 3, 4, 5. I did. Why didn't somebody tell me you lost a carbon? You assumed I would get to it. All right. Thank you for your confidence in me. Yeah, you need to get from the starting material there, you need a dihalide that has 6 carbons. 2, 3, 4, 5, 6. I tried counting correctly. At least there you discover my intentions. If I did it wrong, you can correct it yourself. Yeah, so we deprotonate here. Then we introduce this alkyl halide. It's got 2 reactive ends, but we'll only have 1 negatively charged carbon. At most, we can react with 1 of those. We make the new carbon-carbon bond that gives us this product. We deprotonate again to get this one. We then do the intramolecular SN2 alkylation to give this intermediate. Then we hydrolyze the ester, decarboxylate, and tautomerize, and there we go. All right. Questions about that? Yes?
Yeah, when you deprotonate it the second time, how do you prevent another alkyl halide attachment?
Good question. And the reaction, the answer is this. We only use 1 equivalent of this, so presumably all of it reacts. By the time we get here, we don't introduce another alkyl halide. It's already built into our molecule. And intramolecular reactions are super fast. Others? I saw another hand. No? Okay, that is the one time we're going to go through that in a lot of detail in class. You should be prepared to think through those kinds of questions synthetically. Now, there's 2 things I want to do before we're done. One of them is sort of on brand for today because it's about decarboxylation, and the other involves a series of reactions which I think we can cover quickly next time. That's alpha halogenation of carbonyls. So if it's okay, we're going to stay on topic of decarboxylation, and we're going to talk about how nature does this to make histamine. So histamines are involved in what? Allergies, right? Allergic response. One of the ways that your body makes histamine is from a precursor amino acid. So here is the amino acid. I'm going to draw it in its form that it would exist at pH 7. Here is the side chain, and the side chain has a 5-membered ring containing 2 nitrogens, and this is the amino acid histidine. And your body will convert that into histamine, which has the same basic structure, only lacks the carboxylic acid group. So this is histamine, and if you, heck, I just lost a carbon. Sorry. Are you scandalized by the use of heck? If you are, I apologize. Put it in my end of semester evaluations. Talks like a sailor. A very well behaved sailor. Okay. So this is histamine. Notice that histamine still contains the alpha carbon of histidine, and it still contains the nitrogen, but what's gone is the carbonyl carbon, the carboxylic acid group. And the problem here, though, is that if you're thinking about decarboxylation, we've got the kicker-offer group, you've got the carbonyl carbon, but what's over here, I'm going to highlight in, I'm just going to scribble through, highlight in orange, is currently not a good leaving group. Do you see how if it left, you'd have a negative charge on this carbon and it's not resonance stabilized? So you got a big problem. You need to get rid of CO2, but the group you need to kick off is not a good leaving group, and therefore enters the enzyme, which is called a decarboxylase because it catalyzes decarboxylation reactions. And anytime we need to do magic with amino groups, we're going to use PLP in biology. So recall what PLP is. It's an aldehyde. That looks kind of like this. And then what's attached to that aldehyde is really important because it's highly conjugated and it really is a place where electrons can go. You can think of the left-hand side of PLP as basically being an electron sink. And we've done this before. So what we're going to do is we're going to combine PLP with the nitrogen in histidine via a chapter 14 reaction. We're going to form an imine. And I want to draw that real quickly. Of course, you know, the ammonium nitrogen would need to lose a proton first before it can attack the aldehyde. We'll assume that the enzyme catalyzes that step. For right now, I'm going to abbreviate the histidine side chain as R. And I want to draw the imine that forms when we react PLP with the nitrogen from the amino acid. And I'm getting just a little bit confused. There's a methyl group there. There's a phosphate group here. All right, there's the imine. Notice what that does to our situation for decarboxylation. Pay special attention to that alpha carbon and ask yourself, if the kicker offer, the negatively charged oxygen, kicked electrons down, would all of this be a resonance stabilized leaving group? And you can tell that it would because the negatively charged alpha carbon is now adjacent to a pi bond, which is conjugated to this ring that has a positive charge on the nitrogen. So I'll show you that next time. Then we'll do alpha halogenation of carbonyls, and then we will go on to chapter 18.